From the depths of our planet we look up at trillions of stars scattered across the cosmos, each a radiant beacon in the vast expanse of space. But have you ever wondered about the life cycle of these celestial giants? Stars, much like us, are born, they live, and they die. And some of these stars, in their final act, don't just fade away, they explode with the energy of a billion suns. These are supernovae, the grand finale in the life of certain stars, and they are among the most powerful and awe-inspiring events in the universe. In this exploration, we'll journey together to unravel the mysteries of these stellar explosions. We'll delve into the heart of dying stars, understand the forces that trigger these cosmic cataclysms, and explore the profound impact supernovae have on the universe around them. Prepare to be amazed as we witness the death throes of stars and uncover the secrets they leave behind. Fasten your seatbelts, fellow space explorers, as we embark on this incredible journey into the realm of supernovae. Imagine, if you will, a vast cloud of gas and dust, a nebula, drifting through the cosmos. These seemingly insignificant clouds serve as the birthplace for stars. Over eons, gravity draws these particles together, pulling them closer and closer, increasing their density and heat. As more material collapses inward, the core of this cloud heats up to unimaginable temperatures. This intense heat, millions of degrees, ignites nuclear fusion within the core. Hydrogen atoms, the simplest and most abundant element in the universe, are forced together under immense pressure, fusing into helium and releasing a tremendous amount of energy. This energy, in the form of light and heat, pushes outward, counteracting the inward pull of gravity. A star is born, achieving a state of equilibrium, a delicate balance between the crushing force of gravity and the outward pressure of nuclear fusion. For millions, even billions of years, stars live in this state of stellar equilibrium, tirelessly converting hydrogen to helium in their cores. Our own sun, a middle-aged star, is currently in this phase, providing the light and warmth that sustains life on Earth. But this process cannot last forever. The fuel that powers these stellar furnaces, the hydrogen, is finite. Eventually, the star begins to run low on its primary fuel source. The outward pressure from fusion lessens, and the star's core contracts further, becoming denser and hotter. This is where the star's fate diverges, taking one of two distinct paths toward its ultimate demise. Smaller stars, like our Sun, will eventually shed their outer layers, leaving behind a dense, hot core known as a white dwarf. These stellar remnants cool over billions of years, fading away into obscurity. But for more massive stars, stars at least 8 times the mass of our Sun, their end is far more dramatic. These stellar giants are destined for a spectacular and violent death, an explosion that will briefly outshine entire galaxies, a supernova. Supernovae are not one-size-fits-all events. They are categorized into distinct types, each with its own unique story. Let's explore the explosive death of a white dwarf star, known as a Type 1 supernova. In a binary system, a white dwarf pulls material from its companion, reaching a critical mass. Runaway nuclear reactions ignite, causing a massive explosion. Massive stars end in a Type 2 supernova, a collapse so violent it sends shockwaves across the cosmos. As they fuse heavier elements, they reach iron, which marks the end. The core collapses, creating a shockwave that blasts the star's outer layers into space. This cataclysmic explosion is a Type 2 supernova, the final act of a massive star's life. The aftermath of a supernova is a scene of both destruction and creation. The star that once shone brightly is gone, ripped apart by its own internal struggle. But from the wreckage emerges a new chapter in the cosmic story. For some supernovae, the core of the star survives the explosion, albeit in a dramatically altered state. In the case of Type 2 supernovae, the core collapses under its own gravity, squeezing protons and electrons together until they combine to form neutrons. This creates an object of unimaginable density, a neutron star. Neutron stars are incredibly small, typically only a few miles across, yet they pack the mass of our Sun into that tiny space. A teaspoon of neutron star material would weigh billions of tons on Earth. Some neutron stars spin rapidly, emitting beams of radiation that sweep across the cosmos like cosmic lighthouses. We call these pulsars. But for the most massive stars, those exceeding 20 times the mass of our Sun, the core's collapse doesn't stop at a neutron star. Gravity continues to crush the core, squeezing it down to a point of infinite density, a singularity. This singularity becomes enveloped by a region of space-time so warped that nothing, not even light, can escape its grasp. This, my friends, is a black hole, the ultimate cosmic abyss. Beyond the remnants of the core, the material blasted outward by the supernova explosion forms a magnificent expanding cloud of gas and dust, known as a supernova remnant. These remnants, glowing brightly from the energy released during the explosion, can persist for thousands of years, painting the cosmos with intricate and ethereal structures. Supernovae are more than just spectacular fireworks displays on a cosmic scale. They are, in fact, essential players in the grand cosmic drama, shaping the universe we know and contributing to the very building blocks of life itself. Think of supernovae as cosmic recyclers. Stars, throughout their lives, fuse hydrogen and helium into heavier elements like carbon, oxygen, and iron. But it's during the intense heat and pressure of a supernova explosion that the heaviest elements, those beyond iron on the periodic table, are forged. Gold, silver, uranium, all these elements and more are created in the crucible of a supernova. These elements are then scattered into space, enriching the interstellar medium with the raw materials for new stars, planets, and even life. The shock waves generated by supernovae can also trigger the formation of new stars. As these shock waves propagate through vast clouds of gas and dust, they compress the material, prompting the gravitational collapse that leads to starbirth. In a sense, supernovae, in their death throes, give birth to new generations of stars and planetary systems, and there's more. Supernovae play a crucial role in helping us measure the vast distances in the cosmos. Type Ia supernovae, those involving white dwarfs, are particularly useful in this regard. Because they explode with a predictable amount of energy, astronomers can use them as standard candles, measuring their apparent brightness to determine their distance. This technique has been instrumental in mapping the universe and understanding its expansion. Throughout history, humans have looked up at the night sky and witnessed the awe-inspiring power of supernovae. These celestial events, though transient, have left an indelible mark on our collective memory. In the year 1054 AD, Chinese astronomers recorded the appearance of a guest star in the constellation Taurus. This guest star, visible even during daylight for nearly a month, was actually a supernova explosion. One that created the magnificent Crab Nebula, a supernova remnant we can still observe today. In 1572, Danish astronomer Tycho Brahe observed a new star in the constellation Cassiopeia. This supernova, now known as Tycho's supernova, was so bright, it was visible to the naked eye for over a year. Brahe's meticulous observations of this event challenged the prevailing view of the cosmos, which held that the heavens were unchanging and eternal. And then there's Kepler's supernova, named after the famed astronomer Johannes Kepler, who observed it in 1604. This supernova, the last one observed in our own Milky Way galaxy, was visible for over a year and provided valuable insights into the nature of these stellar explosions. More recently, in 1987, astronomers witnessed a supernova in the Large Magellanic Cloud, a nearby dwarf galaxy. This supernova, dubbed SN 1987A, was the closest supernova observed in centuries and provided a wealth of data for scientists studying these events. These are just a few examples of the many supernovae that have graced our skies throughout history. Each explosion, a testament to the power and beauty of the cosmos, has deepened our understanding of the universe and our place within it. Supernovae, those breathtakingly violent explosions that mark the end of a star's life, are not merely destructive events. They are, in a very real sense, the engines of cosmic creation. They seed the universe with the heavy elements that make up planets, people, and everything we hold dear. Every atom of oxygen in your body, every bit of iron in your blood, and every gold ring on Earth, all were once formed in the heart of a distant supernova explosion. We are, as Carl Sagan famously said, star stuff, forged in the crucibles of these cosmic events. So the next time you gaze up at the night sky, remember the supernovae. These celestial wonders remind us of the interconnectedness of the cosmos, the constant cycle of death and rebirth, and the awe-inspiring beauty of the universe we inhabit. Supernovae are violent yet essential events in the universe. They create new elements, shape galaxies, and reveal secrets about cosmic distances. Every atom of oxygen in your body, every bit of iron in your blood, and every gold ring on Earth, all were once formed in a distant supernova explosion. We are made of star stuff. Carl Sagan.